Welcome to The Explainer. Today, we're taking on the messy, totally chaotic realities of real-world problem solving. We're going to explore how practitioners navigate those tricky environments where requirements shift, boundaries blur, and standard engineering approaches, they just aren't enough on their own. When those standard approaches fail, the stakes are absolutely incredibly high. Think about projects that just stall for years, literally millions of dollars wasted on solutions nobody actually needs, or engineered systems that just flat out collapse the moment they face real human behavior. Well, that is exactly what we're here to fix. Okay, let's dive into this. Have you ever found yourself in a situation where just figuring out what the actual problem is feels like a massive hurdle? Trust me, you aren't alone. Long before a formal system is even built, practitioners face this absolute whirlwind of concerns, conflicts, and perceived needs for improvement. Picture a tangled global supply chain suddenly failing, or a sprawling, super messy legacy software migration, where 3 different departments completely disagree on what the ultimate goal should even be. That kind of chaos, that's exactly what we're looking at today. To make sense of all this, we've got a clear path ahead of us. First, navigating complex situations. Second, the systems thinking bridge. Third, what systems thinkers actually observe. Fourth, how systems thinkers think. Fifth, turning theory into practice. And finally, number 6, limitations and responsible use. All right, starting with section 1, navigating complex situations in our unpredictable reality. So the crucial point is, when we talk about complexity, we're actually dealing with 2 totally different beasts. System complexity is mechanical. It's all about the interdependence, the feedback loops, and the sheer scale of the system itself. Think of a commercial jet engine, right? That is system complexity. It's got thousands of parts that all need to work together perfectly. But situational complexity? Wow, that is highly human. It arises from ambiguity, uncertainty, and conflicting values. Picture the fierce arguments between engineers, executives, and financial officers about how to redesign that jet engine to be cheaper without sacrificing safety. That is situational complexity. It's about the immense difficulty we face in just making sense of what's going on, way before a system is even defined. Moving right along to section 2, the systems thinking bridge, going from chaos to structure. Let's define our core concept here, because systems thinking is not merely thinking about systems. It's a disciplined orientation for inquiry, sense-making, and action. It's a highly developed, super practical capability. So this isn't just some abstract, theoretical buzzword to throw around in your next meeting. It involves concrete habits of mind and real practical judgment. For a practitioner day-to-day, this means stepping back from the immediate fire drill to ask fundamental questions about context. It's that conscious choice to stop looking at a single broken gear and start looking at the entire factory floor to figure out why gears keep breaking in the first place. And this brilliantly illustrates how this capability functions as a literal bridge. On one side of our reality, there's that ambiguous, uncertain, complex situation. The arguments, the vague requirements, the chaos we just talked about. Well, systems thinking acts as the central hub, connecting that chaos to an actual solution. By using active sense-making, exploring where boundaries lie, and recognizing underlying patterns, practitioners cross the chasm from human confusion over to disciplined action, things like formal modeling and architecture. Without this bridge, engineers might build a structurally perfect solution to the completely wrong problem. Systems thinking essentially takes the messy human experience and translates it into a language that formal engineering can actually use. Okay, section 3, what systems thinkers observe, the features of systems. When systems thinkers step into a brand new environment, they are immediately scanning for recurring features. They know for a fact that connections and dependencies often matter just as much as the individual parts themselves. They're actively observing how structure influences behavior over time. They look for feedback loops, where effects loop back around to influence their causes, kind of like a thermostat that turns off the heat once a room gets too warm. And they watch for emergence. Emergence is those system-level properties that arise from interactions and simply cannot be found by looking at the individual elements alone. To put it simply, emergence is like a massive city traffic jam. You can't understand a traffic jam by pulling over a single car and studying its spark plugs, right? The jam only exists when all those cars interact on the same road at the exact same time. Which brings us to section 4, how systems thinkers think. Processing internally. So we know what they observe out there in the real world, but internally, they rely on specific cognitive habits to turn abstract theory into practical, everyday inquiry. Relational thinking, for example, focuses on connections rather than isolated elements. Dynamic thinking forces them to consider how situations change over time, especially when there are tricky delays between a cause and its visible effect. But boundary thinking is perhaps the most powerful tool of the whole bunch. This is the habit of constantly questioning what's been included or excluded in a problem's framing. Think about it. If a commuter train is running chronically late, where exactly do you draw the boundary of the problem? Is the boundary just the train's engine and the maintenance crew? Or does it include the scheduling software, the seasonal weather patterns, and the passenger boarding behaviors? Changing the boundary changes the solution entirely. And systems thinkers, they are constantly testing those borders. Let's move to and see how this builds into Section 5, turning theory into practice across the lifecycle application. First up, we absolutely have to clarify a vital distinction. System science and systems thinking are closely related, sure, but they are not identical, and honestly, engineers confuse the two all the time. System science provides the foundations. It develops the formal knowledge and general, universal principles about how complex systems behave. Systems thinking, on the other hand, is the active, human capability to use that scientific foundation for real-world inquiry, decision-making, and intervention. It's kind of like system science is the laws of physics, and systems thinking is the real-time intuition a pilot uses to fly a plane safely through a massive storm. You literally need the science to build the plane, but you absolutely need the thinking to navigate reality. And we see a very similar distinction between systems thinking and modeling. A model, whether that's a visual flowchart, a mathematical equation, or some heavy computational simulation, is just a formal representation of a system. But here's the kicker. A technically perfect, highly sophisticated model is completely useless if it reflects poor boundary choices or overly narrow assumptions. It's the classic rule of garbage in, garbage out. If you model the wrong problem beautifully, you still fail. And that is exactly why the critical, questioning nature of systems thinking must happen intensely before you touch any modeling software, and it has to continue during the entire formal modeling process. By applying this approach throughout the entire life cycle, practitioners avoid fatal engineering errors. Avoiding premature problem definition ensures you're actually solving the right problem, not just the loudest one. It integrates diverse perspectives across different disciplines and organizations. Plus, it anticipates unintended consequences. Crucially, it connects local decisions to whole system effectiveness, which helps you avoid the dreaded trap of local optimization. Local optimization is when fixing one small component accidentally ruins the performance or value of the entire engineered system. It's literally like putting a Formula One racing engine into a standard golf cart. Sure, you've absolutely optimized the engine, but you're probably going to tear the whole system apart the moment you hit the gas. Finally, we arrive at Section 6, limitations and responsible use, the common pitfalls. Now, systems thinking is incredibly powerful, for sure, but it is not a magical substitute for technical competence. It carries real risks. If you use broad systems language without disciplined inquiry, well, it's just fluff. If you expand your boundaries way too far, trying to include every possible variable in the universe, action becomes impossible. You get severe analysis paralysis. Furthermore, you cannot ignore power dynamics, conflicting values, or lived experiences in the pursuit of a neat clinical system map. Engineering isn't just about math. It's about the people who hold the budget, the communities affected by the build, and the inevitable political friction that pops up during major organizational changes. Using systems thinking responsibly means acknowledging the profound limits of any single perspective. Now, what's really interesting about this slide is how perfectly it sums up our discussion. Ultimately, the value of everything we've looked at today boils down to this. Systems thinking does not remove complexity, but it can make complexity more intelligible and navigable. It doesn't magically make hard problems easy. Instead, it gives us the rigorous tools to identify real leverage points and make conscious, informed trade-offs in a world that stubbornly refuses to be simple. So, as we wrap up this explainer, I want to leave you with a really important question. How will you frame your next complex challenge? Before you rush in to build a solution, will you stop to examine your boundaries, look for those hidden feedback loops, and fiercely question your own assumptions? Use the bridge. Thank you so much for joining me, and keep learning.